Okay, so in this class I'm going to review the radial quantization because it's been 2 weeks since last time there was some kind of confusion, so I laid down all the steps already in the blackboard, and I hope this will be enough to clear all the mess that may have been left over from the previous lecture. And then we're going to use this radial quantization scheme to discuss the unitarity bounds that will constrain the spectrum of scaling dimensions of the Hilbert space states, and discuss the operator product expansion and see how it leads to this notion of the CFT data, which it will be just another, you can take to be an alternative definition of what a conformal field theory is. Okay? So let's start the review. Okay? Radial quantization. What was radial quantization? We take our space-time and follow it by concentric spheres. Okay, space the d-dimensional will have s d minus 1 concentric spheres, centered at some origin that I choose arbitrarily, and your point B just as good, doesn't matter. And then again, each one of these spheres will have its own Hilbert space, but since they are connected by a unitary revolution operator, they are always amorphic, so it's the same Hilbert space. And this Hilbert space, these states that live on this Hilbert space we take to be the eigenstates of the dilatation operator. Okay? Our desire to do so, to exploit that ladder structure of the conformal algebra, was what actually originally led to this idea of radial quantization. Okay? And just to remind you, a primary state, the Hilbert space would be primary states plus descendant states. If you recall the conformal algebra, there was the ladder structure, where the ladder structure for the dilatation or scaling operator, where the momentum operator was a raising operator and the special conformal operator was a lowering operator. They raise and lower the scaling dimension of the state by 1 or plus or minus 1. Okay? And then we created this notion of primaries and descendant states. A primary state is just an eigenstate of the scaling operator, which is annihilated by the special conformal operator. Okay, so just like if you forget the vacuum for a moment, it's just the lower energy state. Okay? You could think as the first excited state, okay, of an harmonic oscillator, okay, which is depicted here. A descendant state then is just you pick a particular primary and keep hitting with the moment operator. P mu, P squared, and so on. Okay? And then in this way you can, and of course the vacuum is just a state that is annihilated by the scaling operator. Okay? And of course the vacuum is going to be annihilated by all the conformal algebra operators. Okay? And the picture we have the vacuum, the zero energy state, for example, and then we have, in principle, infinite primary states. Okay, and each primary state defines this tower of descendant states, again by hitting with the momentum operator, and this whole set, this primaries and descendants, we call a conformal family of this given primary state. Okay, so here we have a primary state with scaling dimension delta 1, then the descendant just delta 1 plus 1, delta 1 plus 2, and so on. Okay, here I'm considering only scalar states. Okay, for the most general state will also be labeled by some spin. Okay, some representation of S on D. Okay, but for simplicity, I'm just considering scalar operator, okay? Because I just want to look into the structure of the scale dimensions itself. Okay, but I can have another primary with scale dimension delta 2 different from delta 1, and this 2 will define another tower of descendants, and this will be the conformal family of the eigenstate with scale dimension delta 2. Okay, and in principle I can have infinitely many primary states and infinitely many descendant states and conformal families and so on and so forth. Okay. So, and just like it is in ordinary quantum mechanics, a general state is just a superposition of all these primaries and descendants. Okay? But then there's this question. Okay? How do we create these primers from the vacuum? Okay? This works for creating descendants if we already have a primer. Okay? How do we create these primers from the vacuum state? In ordinary quantum field theory, this is just the analog of this in ordinary quantum field theory is just the creation and annihilation operators. Okay? The create and annihilate states with definite momentum. Okay? Then we write our fields as a Fourier transform with this creation and annihilation operators. And of course, we hit them with creation operators on the vacuum of the quantum field theory, and then we start creating our states. In CFT, what we do is we create these primers by inserting primary operators at the origin. Okay, what was a primary operator? The definition is basically the same. It's just any operator that is annihilated by the special conformal generator. Okay, and we saw, if you recall the algebra, if you take a primary operator of scaling dimension delta at point x, the action of this guy is something proportional to x plus something, it's mu plus something proportional to x squared. Okay, there are no constant terms here. So this told us that any operator at the origin is necessarily a primary. Okay, because if I take this guy at the origin, then x is 0, so this side is 0, identical. Okay, so any operator at the origin is a primary. Okay, and this is the same, and since it is sitting at the origin, at a particular point, we usually call this a local operator. Okay, and how do this work? How do we take? Why do these primary operators at the origin create those primary states? Okay, we can just define it. Okay, I take the vacuum, I act on it with any primary operator of scaling dimension delta located at the origin, and I define this as my primary of scaling dimension delta. And you can check that if you hit with the scaling dimension of the scaling generator, reproduce all that is here. Okay, by using the algebra of the operator. Okay, by using this guy. Okay, that we saw in the previous lecture. Same for D, but it was something like this. Okay, so on. And you can see that if you make this definition, everything just works as it should. Okay, and but the question is I created a state. Is this state a primary state or a descendant state? Okay. To answer this question, you have to look for this operator at a generic point, x, okay? Not necessarily the origin. The definition is the same. If this operator is annihilated by the special conformal generator, at any point, it is a primary, okay? It's a primary operator at any point. And you can then check, by using this, that when you apply this operator restricted, located at point 0 at the origin, then this state will be a primary. Okay? We just can just translate this guy, and applying the translation operator, the exponential, the moment, and so on. You see that this guy is just a primary. But now take the same operator, but take a descendant of it. Okay? If this operator is a primary, then the mu, acting on this operator, is going to be a descendant. Okay? If I act with k nu here, for example, this will be different from 0. So this is a descendant, okay, at any point x. But nevertheless, if I take this guy and locate at the origin, it will be a primary, identical, okay? But it is not a primary anywhere else, just at the origin. And then if I take this guy, which is a descendant of this one, in general, just as at the origin, and locate at the origin, I'll create an eigenstate of the scaling dimension with scaling dimension delta plus 1. Okay? This operator has scaling dimension delta, and a raise act with the moment operator, the resulting operator will have have the scaling dimension delta plus 1. Okay, just raise its eigenvalue. And I'll have another state, delta plus 1, but this state is going to be a descendant state of this primary state. Okay? I think at least one of the reasons the confusion that arose in the previous lecture was because maybe I did not do this scaffold. Okay? If you take, then again, take any operator, any primary operator at any point. Okay? This, any point x. It is a primary operator, it will create a primary state. Okay? If you look at this operator in the origin, it doesn't matter, it will still be a primary state. Now if you take descendants of this operator, then, okay, it will be descendant. But when you restrict to the origin, you have a primary, and by playing the same game, you create an eigenstate. But these eigenstates are descendant states, not primary states, okay? So you should be careful when saying primaries and descendants. Have to have really clear in your mind if you're referring to primary or descendant states as opposed to primary or descendant operators. Okay? And I did not write it here in the review, but we discussed in the previous lecture. If I just take this operator, a descendant operator, and insert at any other point, as at the origin, I will get a state, but this state will just be a superposition. Okay? We are general state. Okay? But since, again, the Hilbert space is just primaries plus descendants, we see that by acting with these local operators, all possible local operators, at the origin, I create all primaries, I can create all primaries and all descendants. So, the set of all local operators, primary operators they are located at the origin, will create then all states. So we have this isomorphism between local operators at the origin and your Hilbert space. Okay, this was the operator state correspondence. Okay, this was I tried to emphasize in the previous lecture. Is the most, at least the way I understand, this is the most important result from conformal field theory. The most important characteristic signature of a CFT. Okay, this won't be true for any, as far as I know, for any other quantum field theory. Okay, and this has far-reaching consequences. One of them is just the operator state, operator product expansion that we'll come to discuss at the end of the lecture. And it is this state operator state correspondence that allow us to manipulate states on a CFT the way we do, the way we do, say, in Unitarity bounds. Okay, I won't do it too explicit, too step by step, but if you take a closer look, you'll see that those things will be possible because of the operator state correspondence. Okay, so are there still any doubts, any confusion and mess regarding the radial quantization? Okay. What was it? The radial quantization was a choice of quantization, just a choice, but a really convenient one that allows us to exploit the lattice structure to make all of this construction and derive the operator state correspondence. If I wanted to just follow it like in an ordinary quantum field theory, that is taking time slices instead of spheres, and do everything in terms of the Hamiltonian instead of the scaling operator and so on. I don't know, maybe we wouldn't see this operator state correspondence, we wouldn't see these results. And it is these results that make life easier on a CFT. Okay? Is it clear? Is the point clear? Any questions? You have questions?
No, I think sorry, just because you always say that the evolution operator is unitary. So
you have to.
So it's
okay, because of the the eigenvalues are. It is unitary with respect to the, recall that recall that one remark that I made in the previous lecture was that the Hermitian conjugation on a CFT is not like transposition in taking a complex conjugate. Okay, it's not the usual. We use the same symbol, but it is not the same operation. Okay, the operation was to was that of inversion conjugation. Okay, if I take any operator A, then the conjugate operator is just an inversion applied. Okay, it's just inversion conjugation. Okay, and our notion of unitarity in this radial quantization scheme is constructed around this definition. Okay, and you can see that scaling do go to scalings. Okay, if I put momentum here, then inversion conjugated momentum is just a special form transformation and vice versa. Okay. Another way to see this is just to look at the conformal algebra, because if it is the ladder sector, because if it is, they are indeed raising and lowering operators, they must be conjugated to each other in some sense, and it is not on this sense anymore, it is on this sense. Okay? Any more questions? So, I'll be sincere. On this unitarity bounds, I had the computation made neatly, and then I decided to, because we had a period of 2 weeks without any classes and lectures, and then I decided to redo the notes, and then the way I did, I guess I missed some minus sign somewhere around here. Okay, but. Maybe we can spot my side, but there's no problem. The result should be what I'm going to tell you it is, okay? Maybe I'll find it right here, but there might be some minus sign loss somewhere, okay? You can check this on all those lecture notes that I referenced in the first lecture, okay? So, since there are no white chalk here, so might as well use it. Can you read this? Can you read this? I don't know if it's a problem with the blackboard or the chalk.
I can get some white chocolate. You want me to get some white chocolate?
Yeah, it's okay. It's because there are no white chalks here. only carbon ones, so I thought, okay, might as well use them. Okay, might as well start writing something. Can you read this? It looks like part of the name is on the blackboard,
Huh? Okay.
but I guess the chalks weren't that good either. Thanks again. Can I raise this? Okay, so what are these unitarity bounds? It is constraints on the spectrum of scaling dimensions of your Hilbert space states. And how do we find these constraints? Okay, so we take a primary set. Okay, and unitarity means that among many other things that the norm of the state must be positive. Okay, and of course, if this is 0, then yeah, much better. The vacuum state is the only one for which that has norm 0. Okay. We may have the generate vacuum and so on, but okay, we're not worried about the CFT. Okay. So any of the states should have a positive norm. Okay. And how do you exploit this condition to constrain the spectrum of those deltas? We use, of course, the ladder structure of the conformal algebra. You write this as this, for example. Okay, so like I'm just raising the normally negative value. Should obtain the same thing. Okay, I'm not worried about degeneracies, and you're worried about something.
This
Can you read it?
Yeah, so this will be one. No, I mean the state should be what? Why is it?
Oh yeah.
Okay. Ah.
No.
Just. I mean, state should be.
It's 0. The norm might be should be positive.
No, but I mean, so normally all states are normalized if you normally take in vacuum is just a state.
Oh, okay, yeah. I'm also not worried about normalization.
Yeah, okay, but it shouldn't be. Or I think it should be 0, no?
Can be any number.
Yeah, but
Not 0.
not 0. I mean.
Okay, we're just saying this.
Yeah. And this also applies to the vacuum, no?
Yeah, sure. Yeah.
Yeah. Yeah.
Okay, let me just.
Yeah. Okay. Yeah.
Okay, unitarity means that the states must have positive or not. You want to say something? So I take that state is in a product, and I will write it like this. Okay. The index structure doesn't matter much. Okay, I could have taken mu, but at the end it just complicates the algebra in the middle, but the results are the same. Okay, so I just take like the same index like contraction, and it'll be a bit easier. And this is because I'm not worried about any degeneracies and so on. So I'm just taking the state, raising the index, okay, producing the sentence, then lowering it back. So it's the same state. Okay.
So there could be some factor normalization, some number actually, you know, if I look with harmonic oscillator or not. So, okay, whatever. Yeah. there might be.
But if you have the explicit wave functions and so on, then I suppose you could say, okay, now I want to normalize this one.
Yeah, okay, probably it's somehow. Yeah.
Okay. Then what I do, okay, if this is a primary state, okay, this is a supposition, then we know that, okay, mu delta is 0, okay, and also if you want, okay, this should be 0 too, okay, it's just a conjugate, in that sense that I explained, okay. And so what we do is just commute these guys to bring to one height. So this is just commute plus, okay, I'll write it, but of course this is 0. Okay, this one I have it, so this will just drop. And this commutator, if you recall, we did something like, I think this maybe where I missed it, minus 7, something like this, 2i. That will be, okay, there is a metric here, but since I took this contraction, we just reduce like the trace, so it is the, just need the dimension of space, okay? See that? Yeah. So it's just a number. D, the scaling operator, there would be some contribution here proportional to the rotation generated, but since I'm taking that trace, this is 0 because it is anti-symmetric. Okay? Just and also I'm taking scalar fields, scalar states, so this will be 0 anyways. Okay? And the condition that it should be positive. And we know the action of this guy. I guess it was here that I lost the minus sign. Because, I guess it was a minus here. The point is you have to be careful because there's a really subtle minus sign when you're trying to. How do you create these states? You do that again. You act with operators at the origin and so on. Primary operators at the origin. And that is a really subtle minus sign when you're doing the conformal algebra on operators versus when you're doing the conformal algebra on the states. Okay? And this is a minus sign that I lose all the time. Okay, so it might not look like it, but I guess there was a minus sign here for this commutator, or maybe when this guy is acting in this one. Okay? The point is that there'll be some minus sign that I lost here from one or the other. But the point is this will become, okay, there will be an I, then a minus I here, or vice versa. So the I will drop. 2d delta. Okay, it's an eigenstate of scaling operator. Same thing. Now these are all numbers. Okay? And this d is just the dimensionality of space. Of course, it's different from 0 and it's positive. So I can just drop this guy. So this condition translates into this condition. Okay? The unitarity, the positive norm of this state translates into the condition that they must have positive scaling dimension. Okay? This is what we call and this terminology will become clear in just a minute. Okay? This is what is called the level 1 level 1 bound. Why can't level 1 just become clear in a minute? I just want to remind you that we already knew this should be solved on a physical grounds because recall that any correlation functions, just take the scalar, okay? True identical scalars. The correlation function was something like this. Okay? If delta was negative, then this would be something like this. Okay? Right? This guy is now positive. And so correlations will grow with distance, and this is generally not accepted. Okay? We expect correlations to decay with distance. So I guess I anticipated this when we were discussing the correlation functions, okay? And this is the how it arises in the context of radial quantization and the operator state response. Okay. So what was this level 1 that I called? Just refers that I played this game of resetting, of raising and lowering the operator only once. Okay, so this is level 1. What is a level 2? Bound. I already know what it is.
What's the connection between these and the work function?
Between?
What did you say about the work function?
Okay, we saw that the 2-point function, I'm thinking Scala is useful, as you can see, has this form, okay? 1 over the r squared, r some dimension, some power, okay? And this power is just the scaling dimension of these fields. Maybe I should have, these fields have scaling dimension delta. Okay, the operators. Okay, I think those operators. And from this 2-point function, we can already expect that the scaling dimensions for a healthy theory must be positive. Because if it was negative, then the correlations will grow with distance. Okay? And in a healthy theory, they should decay. Okay? So we could already expect and anticipate this, or derive, if you want, this bound on physical grounds. Okay, this is true for any 2-point correlation functions of scalars, spinors, whatever you want. Okay? But the point is, okay, I did not call this level 1 bound for nothing. Okay? There is a level 2 bound that is stronger. Okay? And what is this level 2 bound? It is, okay, put the state, and I do the again twice. So, again, the choice of index, how you match this index, usually doesn't matter much. So, but, I'll do something like this. Okay, I raise twice, and then I lower twice. It's the same state. This should be part. Okay, and the, okay, now the algebra gets, can get a bit too long, but it's the same thing. Okay, we just try to commute this case to the right and this to the left, using the conformal algebra, lecture 2. And the point is, if you do everything correctly, the end result is that the scaling dimension, this positive condition, just like this one, translated to a constraint on the scaling dimension that is, for these Scala states, it is like this. Okay? And D is the dimension of space. Okay? And this because space plus time, Fermi constant, okay? Dimension of space time. No, that's the point. I think there's an equal here. Because there is an equal on this bound. At least on this one. Well, when we put as prepared, I did not worry about that. Because we have only 0 states. One way to see this is because, okay, just take, this will be observation. Okay? Just take the free Scala field. Okay? No mass, so this is, and take it D in 2 dimensions. Yes. The Scala field is conformal in 2 dimensions. It's not 2 dimensions, it is conformal. And it is free and it is conformal. Okay? So in this case, the scaling dimension should coincide with the mass dimension, okay, that we do on our counting, our organization group, and so on. And if you do this, the mass dimension is just 0, okay? Okay, I write the action instead. Okay, this integration, okay, that is minus 2, 2 derivatives, that is plus 2, because the Scala field has mass dimension 0, okay, which is consistent with this bound if I have the equal, and consistent with this bound if I have, okay, they'll say the same thing, okay, because d over 2 will be 1 or minus 1, okay, this trivial case, the level 2 bound is the same as the level 1 bound, okay, and the series is perfectly healthy. It is trivial, it doesn't have anything fun about it. Okay. So there is the bigger, there must be the bigger equal. Should be 0 or positive.
okay, I mean, I don't know. I mean, for me, like a state that would be, so it's orthogonal to itself, its norm vanishes, doesn't really make sense to me, but I mean, okay. What might be the, I mean, from there to there can be still the issue that, well, P could still emulate.
What issues?
No, okay. I mean, I'm not sure if you. Okay, I don't say anything. I have to think
I
about
think that a general state can be zero, but the vacuum does not can be zero. Then.
the norm is 0.
I don't know.
You're talking about states in the Hilbert space? This norm
Yeah,
0?
those are states on the Hilbert space. Those are parameters. It is one of the states of the Hilbert space.
This norm 0?
That's it.
Okay.
Split.
Okay.
I'm confused.
Yeah. Yeah. Well, let's go back to the next.
Just this question, this issue, just do not pop on my mind. Any other questions related to this one? Any comments? Questions about something else? So we'll just leave this observation here. And actually, if you do this level 2 bound, you will also find this condition. There again, because you find something like this. Outs and minus. You find something like this. So you find again the level 1 bound, and then you find this new condition. Okay, if you do this game correct. And then you might expect that, okay, so I can keep playing this game. Okay, I can find a level 3 bound, I can find a level 4 bound, and so on, and then maybe I can impose infinitely many constraints on my scaling dimensions, but the point is, it stops here. Okay, if you try to make a level 3 bound, you just find this constraint again. And the reason is because of the conformal algebra. Okay, the manipulations here is just like you're manipulating these operators to bring the special conformal generators to the right and the momentum generators to the momentum operators to the left. And every time you do a commutation, you produce either a scaling generator or a rotation generator. And from the level 3 forward, you just keep producing the same thing. So you just keep producing power of these guys. So you'll find the same conditions again, and the game stops at the level 2. Okay? You could, if you want, you can check for yourself. I guess it becomes pretty clear. If you could be some kind of exercise, if you want, try to derive this bound in level 2, and you become a big computation. But if you look closer, you can see, you can start predicting that if you try to play the same game and level 3 bound, you just find the same thing over and over again. You're just producing the same generators over and over again. Okay? Because then you produce scaling dimensions, and then you need to compute the scaling dimensions with P and Q. You just find P and Q again. Okay? That's the algebra. The same thing for the rotation matrix. Okay? You commute M with P or Q, just obtain P and Q. Obtain M again. You obtain P and Q again. That's right. Yeah, you obtain M and Q. P and Q again. So we just try producing the same things over and over again. Okay? So that is the reason why it stops at level 2. And this is for scala, okay? So and the result is for scalas. It is the condition. And then you could start doing the same stuff with fermions and vectors, okay? And for this case, you cannot ignore the rotation matrix at level 1 bound, okay? At this point, there's an M menu over there, and just play the same game. Okay, you find that for spin half, the bound is v minus 1 over 2, okay? The 2 divides everything, so it's different from the scalar. And for spin 1 and up, the bound is just d. For spin s greater or equal to 1, is d plus s plus spin minus 2. Okay.
We have using this result.
Fermions, I said direct fermions. If you take 4 spatial dimensions, 3 half coincides with the mass dimension of a free. Okay, it coincides with the mass dimension of a fermion in 4 dimensions. Okay. If it is free and has no mass, and it is conformal, then it coincides with this, like similar as it happened here. Okay. And this is the result for higher spins. Okay, and of course they are divided in the same way, but again they should become more tedious because you have to commute with the rotation method and so on and so forth. Okay, so there is not much point from deriving everything here like all over again. Okay, you can understand again pretty easily from here. Okay, everyone you just already played too much with normal product operators. Okay, so any questions about the Unitarity bounds? Just another comment. If you do want to derive these conditions, I guess this condition for the higher spins, you find this already at level 1, don't need to go at level 2. And this one, I'm not sure. It's either level 1 or level 2 condition. Any questions? We're going to move to the operator product expansion. Okay, and final remark. This is for the theory to be unitary, have a unitary CFT. If you're dealing with a CFT that do not meet this criteria, it doesn't mean it is useless. Okay, it could just be an effective field. Okay, that is perfectly fine at some energy scale. Okay. But if you do want a unitary CFT, then you must meet this balance. I already told you at the end of the previous lecture what an OP is, right? I'm not sure now. I guess I just told you it is this, but
Yeah.
okay, so you have some this you already know what to expect, right? But okay, then let's construct the EOP. Okay, I'll just refer to OP. Okay? It is what is referred to in the literature. For sure. What is again? Okay. Consider this state, this following state. State psi. Okay. Important thing, the operator state correspondence already applied here. Okay. Because I'm saying I produce a state from operators. Okay? This one I inserted that this O2 need not be at the origin, but it is there just for simplicity. Okay? So consider this state. Okay? It is possible that the state operator correspondence, and this state in general will just be an expansion in the eigenstates. Okay? It will just be a superposition of primaries and descendants with some coefficients here. Okay? Just like quantum mechanics. But I already know that I can produce these eigenstates from primary operators. Okay? So we trade this sum on the right hand side by a sum over primary operators. Okay. Then there will be some coefficients here that will depend on the particular operator, of course, just like this end. This coefficient will have, in general, some dependence like this. I'll explain just a minute. The operator itself, located like this. Okay, I just used the operators that corresponds that we discussed. I'm trading this sum over eigenstates by a sum of primary operators located at the origin acting on the vacuum. Okay? This x is because of this x. Okay? In a minute I'll just put these two equations together. Okay? See the whole picture. This derivative is just taking into account the descendant states. Okay? I take a primary operator. This is a primary is on the origin. Okay? You can go over here. We recall that one possible primary at the origin is a descendant of some other general true primary, if you want. And this is why this derivatives over here. Okay? We differentiate, then we take the end of the origin, we have a primary. Okay, and this, as we discussed on the review, this will be the descendant states that are contributed to the sum. Okay, so here, so this is an equivalent form to write this superposition. Okay, now join these two equations together.
Yeah. This CO is also an operator, right?
This is a constant. Okay,
Oh.
I mean, they are derivatives. So it has a moment operator inside here. Okay. One of the next things you're going to do, you're going to study the structure of these constants. Okay. But this constant depends on the particular operator that I have here. Okay. Just like I have one constant for each eigenstates. So I have one constant for each primary operator. Okay. And just take this side and this side. Everything is. Again, this zero is just for convenience, okay, future convenience. And what we have is, I'll just drop the back and say for now. It's the same on both sides. And from now on, when I write the sum, I want these OKs will always be on the student's primaries, okay? So just don't keep writing primary all the time. I don't like this. So what have we done? Okay, what have we achieved? We managed to trade the product of two operators for an infinite series of only one operator. Okay, this is what I told you. The operator product expansion was the previous lecture, and this is just the way to derive it. Okay, in a general quantum field theory, without scaling and without conformal symmetry, you also can have these operator product expansions, but there will usually be some an asymptotic expansion, meaning they will converge only in the points that are really close to each other. Another way to put it is just like a deep UV expansion, if you want. Okay. And the point.
You said earlier that we're using O2 at the origin for simplicity. But does that mean that, for example, if we use O2 on X,
At the same point.
yeah, but if we rather see that it's a primary.
What?
But because you need a primary operator, right? So if we guarantee that O2 everywhere is a primary operator, then when we do this OP, we'll get something that's not in the origin, I suppose, but we will have the same form,
This will be one of the points
or
we're discussing. We can
or
we can actually place this guy here. I'll draw some pictures in a moment, okay? Then we can return. Maybe we compare, discuss the convergence. So, would you like have, I don't know, 5 minutes? Okay. Any more questions? Okay, so what I was saying. So, in a general quantum field theory, you can have operator product expansions. It will be just an approximation, a symptotic series. Okay. In CFT, it is an exact representation. Okay. Why? Because of the state operator correspondence. Okay. We know that we can do this at any point x. For x can be as far apart from the origin as you want. Okay. Except for one condition that I'll come to in a minute. And this will work because of the state operator correspondence, which is again an isomorphism between the space of the set of local operators of the origin and the entire Hilbert space. Okay, so the OPE in a general quantum field theory is just an approximation. Okay? It is used to derive those QCD, some rules in general. Okay, and whereas for CFT it is an exact expansion. Okay. The point that I remarked, except for the only thing you must be careful about is, say you have 3 operators. Okay. You have the origin here. Okay, so this would be, say, our O2. Okay, at the origin. I have another point here. The other operator is here. This can be whatever you want. This can be 1 nanometer or just like 1 light year. Okay. The theory doesn't care. As long as they are, this is some rate. Okay, so we have a sphere. Okay. Just like those spheres affiliated space-time on radial quantization. As long as there are no other operators inside the sphere, this expansion is exact. So if I have operators. All the operators are outside here, then the expansion is exact. Okay, and this guy that comes out on the right hand side, this operator that will come on the right hand side, I can place it here, here, here. I can place it here, as long as it does not cross the sphere of any other operator. Okay.
In the correlation factor.
In the correlation, yeah, that's another important remark there. I'm not writing here, but this game only works inside correlation functions. Okay, those are operator statements. Okay, so they are valid only inside correlation functions. But it is the usual practice to not write the correlation function because it is boring. I mean, it's the usual practice on dropping the brackets on the OP because it's important and so on. Okay, but you must keep in mind that everything I'm doing here, I'm doing inside some correlator. Okay, in that case, a 2-point function.
Can I, just to understand the right hand side, I mean the sum, can I understand it that it often is an expansion in orders of derivatives of delta y? So it's, I can think of it, okay.
It's a derivative expansion.
Derivatives.
Okay. Any more questions? So you had the question that I skipped. What? Can you repeat it?
if we change from O2 from the origin to another point.
Two?
Another point.
If I take O2 here and put it here,
Yeah.
then what?
Then will the structure of the OBE be the same or will it change? Or will
The structure will be the same. Okay, this point X that I choose, okay, I could have chosen, say a point Z. Okay, Z could be this point or this point. Could be any of the starting points as well. Doesn't matter, as long as it does not cross any other operator. Okay, if it crosses any other operator, then okay. So I'm just sorry. Before I pollute this blackboard too much. Okay. Since you don't want it on the origin, so okay, I'll put somewhere else. Okay, the origin is here, the O2 is here. My O1 will be some X prime. Okay. And I can do an OPE. Say the only other operator is right here. Okay, there's an O3 here. At y. Okay, so I can do this OPE. Okay, I can do this expansion and place whatever comes out, or whatever operator comes out in this right hand side on anywhere inside, say, this sphere. Okay, just before it crosses, just before it hits this O3. Okay, so I can put it here. I can put it here, I can put it here, I can put the origin if I want, I can put inside one of those, at the same point of any one of those two operators I started with.
But I can't choose its origin itself.
Huh?
I can't use the origin itself.
No, you can put it the origin.
But then is it then a prime? I mean, then again it's a local. Or what? No, sorry.
You're worried about...
No,
yes.
if I take...
You're worried about if I put it on the origin,
Yes.
I would lose the superposition because... You're worried about losing the superposition if I place the right hand side of the origin, because then I'll just select one state in the primary descendant. That's what we're worried about. Yeah. Maybe you're right. I'll check on this. Okay, maybe we cannot put the origin specifically. The reason I'm not too sure because what we're gonna do next, we're gonna use the knowledge we built upon the correlation function, and we'll see that typically we'll just select one, just like this whole expansion will just come down to one term or the other. Okay. But anyways, just be careful, don't say anything wrong. Yeah. Okay. We can place anywhere, maybe not at the origin. No? I believe we can. Okay. Anywhere, so we can place it anywhere. As long as you do not place in some point that is on the same sphere as any other operator. Okay. So what I'm saying is the OPE on a CFT converges. Okay. We don't need to take x close to the origin. No, in fact, in a general QFT, you can only do this is say O1 is here and O2 is just some x plus epsilon. They're really close to each other. That's why it's in a static expansion general QFT. Okay? And intuitively this has to do because if you're on the deep UV, then all your scaling, all of the scalars on your theory are negligible. Okay? So it's kind of a scaling region of your theory. Okay? But it's an approximation. So that's why it is an asymptotic for general quantitative theory. And if you want something specifically, again, there's a QCT, you had those scaling behavior for the quarks and the deep inelastic scattering, like those that was studied by Bjork, I guess, the SLAC. They observed the scaling behavior. This had something to do with this, okay? You're in deep UV regime, so you had some scaling symmetry, but it was an approximation, okay? But on CFT, it converges for any distance as long as you don't cross any other operators. Okay. Any questions? No? The next one then is this. Take a closer look to this coefficients. consider this correlation. Okay. So we usually drop the brackets for correlation points, but I will just write it this whole time. Okay. This is how I did it. Keep this one to origin. And consider this correlation. It is a 3-point correlator. We already have some idea of what this should be from the conformal symmetry alone, okay? And this is just okay, this is what we found what the 3-point function should be only for scalar parameters. Okay, we have the functional form fixed like this. Okay, I just took one of them the origin just to simplify a little bit the structure. Okay. And a structure constant that was not fixed by conformal symmetry. Okay, it is a constant. You just don't know what it is. And 1 through 3 is just actually labeling operator 1, operator 2, and operator 3. Okay. But on the other, this more simply, this can usually be represented like this. Okay. People sometimes say we fused operator O1 with operator O2 into an OB. Okay, and this is usually denoted like this. Okay, and of course you do not mistake this for those weak contractions and so on. Okay, it's different concept. Okay. And the point is, we're gonna do an OPE on this correlation function, okay? Because we can. And I guess I did here between O1 and O2. Yeah, O1 and O2. I'm not using this right hand side for now. Just okay, hold this right hand side for now. Okay, I'm just doing just computing this in another way. Then we're gonna match the right hand sides. If I find the OP right over there, I'm just gonna open up the sum a little bit more than it's open there. And I'm fusing these two operators and putting the operator that will come up here at x. Of course, I'm supposing that the operator O3 is how is this? It's more distance.
Further outside.
Yeah, further outside than this two. Farther outside. It's on the operator. Okay, I'm supposing that this operator is far outside than far apart than these two operators are. In order for this OP to work. They don't need to be for this, of course, but for the OP it's if they were, then I just could do between 2 or 3. Okay? Doesn't matter. So I put it whatever comes out on the side on x. Okay? Since these are constants, I'm just putting them outside.
Maybe it's a question, but can I do the operator product expansion if there's an operator in between? Because somehow, I mean.
And then there are operators.
Huh?
There are operators.
No, I'm just.
No, you mean.
Like, if I would want to do between O1 and O3, there would be an O2 in between. So I could think, well, I could use. I mean, they don't
You
commute,
mean
so
if I
it's
wanted,
not the same.
if I wanted to do this?
Yes, exactly.
Okay,
So I can do it.
you can do it. Okay. As long as then this guy, as long as you can find some sphere that encompasses this two so that this one is outside.
But my question is the operator.
If you need to commute then to no, you don't need to.
But the operator that comes out is to the left or to the right of O2?
The left or the right?
Which matter? I mean,
just
operator is
yeah.
what?
You can do a path into representation of this. Okay, this would be like to measure here whatever fundamental field you have, and this correlator would be just something like this. Okay. Okay. And these guys are just functions.
No,
Okay. If you have fermions, if you have Grassmann variables, you should be careful because
but then there's some time ordering going on, or some ordering. Because if it's just an, okay, maybe but if it's just an expectation value of operators and the operators from commute, it should play a role. Now, if there's some, or I mean, if I have O1 times O2, it's not the same as O2 O1.
The path, okay, this path is a representation of this coordinator automatically
but this
stop
would mean,
or
no, but this
orders the notation.
yeah, but this would mean that it would not be a general correlation function, but a time order correlation function. And then I can, of course,
Not time,
or whatever.
not
yeah.
time, but
Yes.
the ranges of the.
So the expectation value is something like radius order expectation value.
Yeah.
Okay.
So this becomes clearer on the in two-dimensional CFTs because you can go into the explicit computation. Okay, but you're right. Okay. And if it is bosonic operators, then this order here doesn't matter.
Yeah.
But if it's fermionic operators, then we have those minus signs. Okay. But again, what I was trying to say that as long as they're inside the Polish function, they're like functions. Okay. With only the remark about Grassmann functions or fermionic operators, fermionic fields. Okay. Any more questions? Then,
You're doing all three together or just one?
oh no, okay, sorry. This is not the question. Okay, I'm doing this. Okay. This fusion zone is always between two operators. Okay. So if I wrote it like this, because to be exact, I'll be fusing O1 and O3. O2 will be leaving untouched. And the question was about if whatever comes out, do I put it on the side or the side? It doesn't matter. Okay. And the answer to the question was, okay, this is a correlation function. We can give a path into representation that automatically time orders or radial orders, okay, because of radial quantization, these operators. Okay. And if you only, if it's bosonic operators, you can just start commuting them with no problem. And fermionic, you can just pick up a minus sign every time you do this. Okay. So what I'm doing is this, okay, I'm using this two. And I'm gonna obtain some operator, some parameter okay here. Okay, same thing. It's yeah, Radial, so I guess you can go ahead. Maybe if you ask a mathematician, we do the taking product with the operator, so then I have another term of this series. Okay, so what I opened here was what I'm opening here is the derivative structure. Okay, so the next guy should have an index mu, and then we should have the derivative mu here of the same. Okay, let me write it like just make this one here x prime. This derivative is with respect to x prime. And then also take x prime to 0, which is the point I chose to insert my operator. And so on.
In the C case, it's still a function of x.
Still a function of x. I only separated the derivative. Okay? And now, by consistency, this should equal this. Okay? This we know from confound symmetry, this we know from the OB. Is a consequence of the operator state response. but it's not very friendly. I mean, one thing we already know, we know also the structure of the two-point correlators. Okay, that's one thing. But there's another thing that we can do to simplify a bit. That is, I said that this guy can be really far apart. Okay. But since I have scaling symmetry on my theory, I can do a scaling and bring them close together. Why do I do this? So I can make a data expansion and make this look a little bit better. Okay? To compare. I can do this on CFTs because I have the scaling symmetry. Okay, so what I'm going to do is I'm going to do this, I'm going to Taylor expand this guy again. Okay? I'll take x small. Okay, I'll take x close to 0. And of course, doing that is boring, so we're just going to give you the results. But it's really straightforward. Just going to expand that, just be careful. Because just be careful when you're taking derivatives. Okay? Because I take derivative with respect to x mu, but that depends only on factors of x squared to some power and I function in rule. It's a bit annoying, but it's straightforward. And the result is, so I call this 1. Okay. I'm taking x less than 1. We can expand that and we will obtain